coming. This also took place in 2011, which was an incredible year for severe weather. This was a powerful Derecho event back on July 11th of 2011. And this first picture you're looking at here, these are metal power poles or transmission towers that were actually flattened by the wind. And that's a cornfield that was blown down too. And what really, I did an independent study of this event last semester. And what really caught my interest is this event actually peaked in intensity just prior to dawn. And that was probably what the scariest thing about this event was. And this picture was taken in eastern Iowa. So for a basic overview of the event, it traveled from central Iowa all the way to Maryland. It was at its most intense between eastern Iowa and southwestern Michigan in the early morning hours of the 11th. And in Iowa, portions of Story, Marshall, Tama, Benton, and Lynn counties were absolutely devastated by the high winds. And storm survey teams estimated incredible pockets where winds were estimated to be between 110 and 130 miles per hour in the hardest hit areas. Nearly every tree in Garrison and Vinton, Iowa was either severely damaged or snapped off. And so here's a storm track map from the Storm Prediction Center to show you how things were kind of evolving. In the yellow area here, there we go. In the yellow area here, you had an area of thunderstorms develop on the afternoon of Sunday the 10th that moved across Nebraska with a lot of wind and hail reports. And then that same afternoon, there was another area of convection in blue here that went from the Dakotas through Minnesota with a lot of wind and hail reports. And those areas of thunderstorms both weakened during the overnight hours, but at around 3 o'clock in the morning, intersections of some outflow boundaries caused an intense bow echo to form east of Des Moines, Iowa, and that what you see in green kind of took off towards Chicago, and then it weakened over the Appalachians and then kind of redeveloped over parts of Maryland that evening. So this here, what you're looking at, is prepared by the NWS in the Quad Cities. This is a map showing from the survey that they did, and this is looking, this is looking at a series of downbursts that started to the east of Marshalltown and went across portions of northern Tama and northern Benton counties. Where you see the orange, that's where winds were estimated to be in excess of 100 miles per hour. And the dashed red line is where storm survey teams showed winds between 110 and 130 miles per hour. So this is what it kind of looked like on a regional radar scale. You see an area of convection moving out of Nebraska and then another area moving across southern Minnesota. And notice the timestamp here. As we go towards 3 in the morning, a compact bow echo begins to form east of Des Moines. And you can see all those warnings being issued ahead of it. And it rapidly propagates towards Chicago. And once it gets towards southwest Wisconsin, it starts to expand in size into that more classic kind of backward C shape that you see. So some project goals here. I wanted to evaluate the performance of the SUNY Oswego WRF during this event compared with observational data. I wanted to determine if WRF had the capability to accurately predict a widespread convective event such as this. And I wanted to study the environmental conditions and mechanisms that led to the extreme winds in eastern Iowa. So for my methods of study, I used the SPC's mesoanalysis products at 8Z on the 11th, which is when things began to really reorganize. I examined Doppler radar reflectivity and velocity from Des Moines, Iowa, and the Quad Cities with GR2 analysts. And I ran the WRF in a 9-kilometer outer domain and a 3-kilometer nested domain out to 18 hours with the initial and boundary conditions from the NAM for the Midwest and Lower Great Lakes region. And I tested both the Goddard and Thomson moist physics schemes. And then I ran the WRF once again at a 9-kilometer outer, 3-kilometer nested, and a 1-kilometer doubly nested domain out to 18 hours for a little smaller area of southwest Wisconsin and western Illinois, and I tested only the Goddard scheme for that. And I want to credit Dr. Valentine for helping me set up these WRF runs. He was a huge help throughout the entire project. And then I compared the simulated composite reflectivity with the corresponding regional radar for all of these runs. And I also examined the 950 volt wind output over eastern Iowa for these runs. And I compared from the 1-kilometer WRF, I generated a cross-section of simulated winds, and I compared it with a Doppler radar observed cross-section of the storm relative velocity to see if the WRF could simulate a descending rear inflow jet. And then finally, I compared the observed 0 and 12 UTC soundings from the Quad City region to WRF forecasted soundings. So at 12Z that morning of the 11th, when things were really getting going, at 500 millibars, Johns and Hurt, they wrote a lot of papers on derechos, And they classified this classic pattern where you see a big ridge over the southern United States with heights over 595 decameters, and a very fast westerly flow along the northern periphery of it, in excess of 40 knots. They call it a ring of fire type pattern. And you can see here, it looks like in the northern plains there's a bit of a shortwave trough digging down ahead of the system that could have helped to get things going. Now this is really cool to show you. This is an 8Z surface analysis. And notice how from eastern Iowa down through Missouri, temperatures at 3 o'clock in the morning were still in the upper 70s and low 80s. And these blue dashed lines you see here are where the dew points range from 70 to 76 as you head south towards Missouri. So just incredible amounts of heat and moisture for that late at night. And this contributed to extremely high values of CAPE. This is the most unstable CAPE parameter. There's a pocket here of 6,000 joules per kilogram in northern Missouri and 5,000 joules per kilogram extending up into eastern Iowa, and that's once again at 8Z. And the 0 to 6 kilometer shear was pretty impressive as well, but a little further north, it was around 40 knots near the Minnesota border and more 30 to 35 knots across the rest of Iowa and into Illinois. And looking a little lower, the 0 to 1 kilometer shear was pretty good as well, with pockets of 30 knots of west-southwesterly shear and then 25 to 30 knots surrounding that area. So conditions were favorable if you could get a trigger for organized convection to develop. Now what you're looking at here, this is from the 3-kilometer Thompson output. On the left is a simulated WRF sounding, and on the right is an observed sounding. And notice on the right, on the observed sounding, there's a pretty moist profile for about 900 millibars up through 800 millibars. And there's also quite a bit of CAPE. The raw value of CAPE looks like it's 3017 joules per kilogram. And the 0 to 6 kilometer shear was 48 knots at this time at 0Z. What really surprised me was there was actually a lot of directional shear too. You can see that in the strong warm air advection there was winds rapidly veering from southeast to west with height. And WRF did a good job simulating the environment, showing that moist profile up through about 800 millibars. And it's also got the rapidly veering winds with height too, so that was good to see. And this is taken 12 hours later. What I want to mention is this is at the Quad Cities again at 12Z, but the NWS office there told me they got the balloon launch off around a half hour later because they wanted to wait till after the line of thunderstorms moved through. So on the right, you're looking at an observed sounding, and you can see it's very, very stable, which makes sense in the stratiform rain. And the WRF at that time, too, is giving us a very stable sounding. So it was doing a pretty good job simulating the overall environment. Now, on the left-hand side, you're looking at a simulated convection at 10Z from the WRF. And on the right, you have a regional radar at that time. Regional radar is showing a compact bow echo that just intensified east of Des Moines, Iowa. And this is the Goddard run of the WRF, by the way. And this Goddard scheme here at 3 kilometers is showing intense convection over north central Iowa with maxes of 60 dBz. So it's accurate on the strong convection, but it's a little bit too far north and west compared to where it was actually occurring. Now the Thompson scheme at 3 kilometers was having some serious issues because as you can see there's a really nasty thunderstorm complex here, but it's only generating a few rain showers, which was very surprising. I know Dr. Valentine told me he wasn't expecting there to be any difference between the two moist physics schemes. Now this is the 1 kilometer WRF run at the Goddard scheme. And you can see it's also got intense convection at roughly the same spot that the 3 kilometer run had at over north central Iowa, but it's again a little bit too far north and west compared to where it actually was over eastern Iowa. The only really difference is it's just a little bit more detailed. You can almost see a bow shape that it had at 1 kilometer. Now this here, you're looking at the 1 kilometer WRF simulated 950 millibar winds, and this is at 10Z. This circle here, because it's a little clutter that I made for you in red, this is where WRF is simulating winds of 65 to 70 knots at 950 millibars, which is pretty impressive, but these winds are also several counties further north of where they actually occurred. And back here, I wanted to show you this almost looks like an anticyclonic curvature with some spreading out. We were actually wondering if this could have been a meso-high being seen in the stratiform rain. So it was interesting to see that on the WRF simulation. Now this is a cross-section that we made. On the right-hand side, we have a Doppler radar observed cross-section going from the surface to 40,000 feet. The brightest reds are 70 knots, and you can see the winds around 10,000 feet at 70 knots gradually slope down towards the surface. That's the rear inflow jet descending down towards the storm. This was over Tama County, Iowa, at 932Z. And on the left, you're looking at a WRF cross-section of wind barbs and isotachs. And we were hoping that the WRF could maybe simulate a descending rear inflow jet too. And what's neat is when you look around 900 millibars up here, this circle contour that's kind of hard to see is a 60-knot isotach contour. And then that 60-knot isotach contour comes down a little bit towards the surface as you advance further east. And this was going from the surface to 500 millibars vertically. And Dr. B told me he honestly wasn't really sure what would happen because we never tried making a cross-section with WRF before. So it's not a perfect descension, but there does seem to be some sort of descending air taking place. So it was neat to look at. Now this is a radar loop from Des Moines, Iowa. This is showing you kind of what was happening. I want you to look to the north. On the left-hand side here, you have the base velocity. On the right, you have base reflectivity. That's the storms that were moving across Minnesota. And then here comes the other storms that move down to Nebraska. And here, you'll see this outflow boundary dropping towards Des Moines. And right around the time that outflow boundary interacts with this convection here, you'll see it intensifies, it starts to bow out a little bit. You'll see this bookend vortex circulation develops on here, and that seemed to be when things really got going. You started having significant high-end winds. So that outflow boundary seemed to play a crucial role in reinvigorating that old convection. Now this here is taken over Tama County, Iowa. This is a 4-panel base velocity tilt that I made with GR2 analysts. It's actually pretty simple to do. On the upper left, you're looking at the 0.5 degree tilt, which is standard. Upper right is 1.4 degrees. Bottom left is 3.2 degrees. And the bottom right is 5.1 degrees. The brightest orange colors here are winds in excess of 110 to maybe even 120 knots blowing away from the radar. The radar is located here at Des Moines. And notice how as the tilt goes up from left to right, the brightest colors get further and further back within the convection. That's another way that we could simulate the descending rear inflow jet. So I was pretty excited to make that. I had to show you guys that. I thought it was pretty cool. Now this here is taken from the Quad Cities radar. This is at 1016Z. This is about 10 minutes after Vinton, Iowa, in the northern part of Benton County, experienced devastating wind damage and lost an estimated 75% of their trees. You can see a very well-defined rear inflow notch here, where you can see the low reflectivity, and then the high reflectivity values kind of over 60 dBz kind of wrap around that area in a circular fashion. So it's a narrow swath of very organized wind damage. And looking at the base velocity on the left here of winds coming towards the radar, these dark blues are 100 to 110 knots coming toward the radar. So that's a pretty scary thing to see on radar, especially at 5-something in the morning when people are still sleeping. So some conclusions for this storm. The environment leading up to the event was a classic setup for a major derecho with a strong westerly flow around the periphery of a ridge and the approaching shortwave to the north. The high temperatures and oppressive dew point values that persisted late into the night led to extremely high overnight instability, which allowed the convection to persist deep into the night. And the development of a bookend vortex in the rear inflow jet after interacting with the outflow boundary locally enhanced the destructive winds and got things going. Output from the 3-kilometer and the 1-kilometer runs of WRF at the Goddard scheme fairly accurately simulated the event itself and the surrounding environment. But the Thompson scheme, as I showed you, failed to simulate the system at all. And we didn't have time in a one-semester project to look into why that happened, but one hypothesis is that the Thompson scheme was failing to capture that outflow boundary that seemed to be responsible for intensifying the system. Even though the Goddard scheme simulated the system well overall, the convection and associated high winds tended to be too far to the north and west, and that was a persistent occurrence. WRF showed that it had the capability to accurately simulate a major convective system, but there really wasn't much difference between the 3-kilometer run and the 1-kilometer run. Dr. Valentine asked me a neat question. That was one of the goals of the project should be to see if a 1-kilometer run is even worth doing. And as I was showing you, the simulations were pretty much in the same spot. The only difference was it was a little bit more detailed. You can almost see a bow feature in the 1 kilometer. But other than that, there wasn't much change. In the wind output, I believe the 3-kilometer wind output at 950 millibars had 65 knots, and the 1-kilometer wind output at the same level had about 70 knots. So that wasn't too much of a difference. So in the future, I'd like to use the initial and boundary conditions from the rock to run the warp at a 9-kilometer outer and 3-kilometer nested domain for that same area of interest and test both moist physics schemes again. I'd possibly like to run the WRF without a convective parameterization scheme and see what happens. We use the Cambridge scheme, which was already in the model for this case. And I'd like to determine why the Thompson scheme failed to simulate the system, because that was fascinating. I just want to leave you with a couple pictures. This is after sunrise what Vinton, Iowa looked like on one street. You can see pretty much every tree was either topped or severely damaged in some way. Luckily, these homes got missed. And there was more than one street in the town that looked like this. They lost 75% of their trees, and they had a massive replanting effort. And they even had to come down the streets with tractors. A lot of people in this area were out of electricity for more than a week as a result of this storm. So I'd like to acknowledge my wonderful professors, Dr. Valentine, Dr. Skubas, and Dr. Steiger, for helping me with the project, answering any questions I have. And Dr. Valentine really taught me about running a model because I had never done it before. So the whole project was a learning experience for me. And of course, my friends Dylan Ulrich, Andrew Januszewski, and Jake Mulholland, they had done stuff like this before, so they helped me along the way. They gave me advice and helped with anything I needed. And I'd like to acknowledge Rich Thompson at the Storm Prediction Center for helping me recreate those mesoanalysis projects. So that's all I have, and I'll take any questions. Yes?
So you were running work at 3 kilometers with the convective scheme?
Yeah, we ran it with the convective parameterization scheme. And then, like, towards the end of the semester, Dr. B mentioned that we'd see some differences if we didn't have a convective parameterization scheme in it. But it was almost November. We didn't have time to run it again. But we thought it'd be cool to maybe run it without one at some point.
Yeah, because at 3 kilometers, certainly a convective storm of that size probably would have been pretty well resolved.
Okay.
So.